Ready? Good afternoon, and thank you for joining us in this afternoon session. Today, we have the famous Eric Johnson. He's here to present to us on destroying long-lived cloud credentials with workload identity and federation. And I'm told this is a very powerful session and usually runs over with lots of questions. So welcome to the party, folks.
Thank you for the intro. So I was just outside. I appreciate you all coming back inside after the lunch break because it is gorgeous outside. So it was difficult for me to return, but cloud credentials and workload identity federation is a pretty hot topic these days. So I'm excited to come present this to you today. My name's Eric Johnson. I've been in the world of kind of cloud and DevSecOps for roughly 10 to 15 years. I come from a development background, primarily, so I did a lot of work with application security and really building systems kind of in a more financial, regulated environment is where I come out of, at least on the tech side. I co-founded a company called Puma Security about 5 or 6 years ago, and I've been a SANS instructor for over 10 years now, where I currently am an author for 3 different cloud security courses focused on security automation, enterprise cloud security architecture, and kind of cloud security governance and misconfigurations. So the topic today really covers almost all 3 of those areas, or at least the demo and the project I'm going to walk you through. We'll go through a little bit of CI/CD, and then it's going to authenticate from an Azure VM out into an AWS and a Google Cloud project/account to show you how we can do all of this with long-lived credentials, which is kind of the anti-pattern these days. And then we'll take a look at how we can accomplish the entire thing without using any long-lived credentials. So before we jump in, disclaimer slide. This is the part where I tell all of you to read all the stuff on here and then nod your head at me that says, yes, Eric and RSA are not liable for anything that you might do with this information as you walk out the door. Is everybody good with that? Now, level setting with you, I'm going to introduce you to an open source project here in a couple of minutes, which does have some purposely vulnerable demonstrations in it. You are free to take that, fork it, and run it in your own GitHub org or personal GitHub account when you walk out of the door. So as part of this disclaimer, I just want you to be aware of, I am purposely dumping credentials to an Azure subscription out into a GitHub Action log file, which can result in some problems if you make said repo public. So be careful if you go play with this. I'll walk you through how that's all happening here as we dig into the presentation. Let's start with the problem statement. So I wanted to show off workload identity federation in all 3 clouds. The capability exists everywhere. What I want you to understand is the architecture that we're really going to be dealing with here for the next 45 minutes or so. So in this hypothetical cross-cloud system that I put together, yes, I know that Azure has storage, but that would defeat the whole purpose. So what we're going to set up here is a GitHub action. That's our CI/CD system. That's going to be running Terraform that deploys a virtual machine into the Azure cloud. And from a requirements perspective, pretend that someone said you need to architect this system to let that Azure VM go talk to an AWS API to get data out of S3, and then to go talk to Google Cloud Storage to pull data from GCS, which is their equivalent storage option out in the Google world. So in order to solve this problem from an architecture perspective, you've got a couple of options here. The first option is the more historical way that we might solve this problem, which is creating long-lived credentials in Azure in order for GitHub to authenticate to the Azure subscription, and then creating AWS access keys in order for that Azure VM to communicate with the AWS API, and then creating a Google Cloud Service Account key file in order for the VM to talk to the Google Cloud. And that's how we would have done this for several years leading up to the point where we realized this was a horrible idea. And we'll get into some of the why here in a bit. About halfway through, we're going to switch gears and pretend that we had all of this OpenID Connect workload identity federation knowledge prior to making this decision. How could we redo it? And how could we make this a little bit better and eliminate those long-lived credentials that are out there in the world. Everything I'm going to show you today is in an open source repo. I just made it public about an hour ago while I was sitting in the hallway out here just on the floor going through this. So it's available to you. What's inside of it is a lot of Terraform configuration for bootstrapping all 3 clouds with the setup that I'm going to show you. And also GitHub Pages, little Make Docs wiki, which allows you to go in and just follow some step-by-step instructions on here's the commands to run, here's how to grab the Terraform output, feed that into the GitHub Action secrets, and then that will just kind of bring this whole ecosystem up to life inside of your GitHub org. So you can redo all of this when you get back to work or when you get back home, at the end of the conference. Don't feel like you have to take pictures or record any of this stuff because it's all out there in that repo for you to play with whenever you have time or want to go mess around with it. So everything I'm showing you is in that repo. Let's talk about option A, the bad way to do this. How many of you have created a long-lived credential in the cloud before in order to authenticate systems? If you're not raising your hand, you're either lying, or no one has told you that they did it, so you just don't know about it, or maybe you're really lucky and you just started using the cloud and realized that was a bad idea. But for a long time, this is all we had. You had to generate these access keys or these API keys or these tokens, depending on the cloud you're working in. The resource in the cloud that you'll find these attached to depends on which cloud you're playing around with. In the AWS world, you'd create an IAM user and you generate access keys. And then you would give those to a human or some system, and you'd authenticate using those access keys. In the world of Azure, you'd go into the Azure Active Directory tenant that you're working with. You'd create an app registration. And on that app registration, you'd go to the service principal credential section. And then there is an option there. Do you want a certificate or do you want a client secret? And those are both long-lived credentials that allow you to just authenticate as that service principal. In the Google world, everything's a service account, and you create a service account key. It's just a private RSA key in order to communicate with the cloud using that private key. So if we were going to architect all of this, going back to our diagram, where would you have to put these things? You'd go to Azure, you'd generate that client secret, and what you'd normally do is put that in a GitHub Actions secret, which is a special secret storage area inside of that CI/CD system. And then as the GitHub action runs, it would read that secret value and it'd do an AZ login with the client secret in order for Terraform to talk to this Azure resource group that we need to throw this VM into. So that's secret 1. Now the Azure VM, remember, has to talk to AWS and Google. So on that Azure VM, that's where you would find the AWS access keys as well as the Google Cloud Service Account key that the VM would need in order to talk to S3 or GCS. So that's where all of those things would live in order for the first or the original setup to work. What could go wrong? It's the age-old security question. Now, it turns out this has been so problematic. There is an entire MITRE attack for cloud technique dedicated to what I just showed you. Has anyone found these credentials out in the wild before? They're everywhere. Now, a lot of folks have tested this, some on purpose, some on accident. Has anybody seen any of the stories from the world of public GitHub repos where you accidentally throw some access keys out into a public repo and then suddenly you have crypto miners running in your AWS account? And AWS gets mad because you've racked up a $20,000 to $30,000 bill in a very short period of time. And now GitHub finds those events, and GitHub will send you a nasty email that says, hey, we just detected this key in here, and we notified AWS, and then they attach this quarantine role to that IAM principle that says deny ***, essentially. It tries to stop that user from doing anything until you just figure out what happened. So that's one way that we can attack that. That would be the version control path. What about bash history? Do you think there's any creds in bash history? I guarantee you there's some in my bash history on this machine from just doing the demo I'm about to show you. I exported some Azure credentials into environment variables, and those are going to live there until I kill the terminal session, but it's bigger than that. If you compromise an application or a VM or some running workload. Normally in the ENV, you're going to find those sorts of credentials because the application needs to read them in order to authenticate to a cloud provider API. So you'll find a lot of those creds there. There's also the instance metadata service. How many of you have played around with the instance metadata service before? So this is kind of a built-in mechanism for cloud resources. Think virtual machines, functions, app services, container services, things like that. As you spin up an identity, you can attach it to a VM and say, these are the permissions I want this VM to have when I'm running some process on that virtual machine. You can find credentials in there. They're temporary ones, but that's another popular place to go look. We're actually going to leverage that as part of our phase 2 architecture on the Azure VM. We're going to use that for OpenID Connect authentication when we get to that point. So places that you should be looking for these things. Now, Team TNT wrote some cloud-specific malware. Did anybody see that article come out? They were looking at the instance metadata service, as we just talked about, for credentials, because that's a really easy way to get access to cloud provider APIs. Overall, if you want to hunt on a VM for creds, you're going to look in the .aws directory. Who do you think that one belongs to? This is pretty easy stuff. The .azure directory. And Google's actually the only one that wasn't completely obvious with where they're at. There's the config directory /gcloud. So you've got to go a directory deeper to find those Google Cloud credentials. And then you just have the SSH directory, popular place to find some of those private keys that might get you access into some sort of cloud environment. As far as environment variables, this is just a very simple example from the ENV, and I'm just grepping for AWS things. And if you dump ENV in a Lambda function, for example, or on some VM, and you find AWS access key IDs, secret access keys, and session tokens, you pat yourself on the back, you've done a great job hacking today, you're good to go. You take those and you run with them. So those are the sorts of places we'll find these things. How bad is the problem? Now this is fun. So a couple months ago, I'd say back in January, I saw an article from Tom Forbes that said, I just, for giggles, scanned all of the Python package index for hard-coded, kind of static, long-lived credentials. Nobody would put these in a package manager, would they? So the packages, just if you haven't, decompiled or reverse engineered one of those, they're really just kind of big zip files. So if you pull a package down, you can decompress it. And what Tom did is wrote a little script that went through, looked for some of those pattern matches for AWS and said, okay, we've got 57 valid AWS keys that we found just in the Python package index, a publicly accessible package out there in the world. 11 of them were root access keys. That's concerning, yes? Okay, that's the state of kind of where we're at right now. The Node package manager. Now, Aidan Steele did this. It's been a couple of years, so perhaps it's better now. If I had to guess, it's probably worse, actually. And what Aidan did is very similar, ran the script, 117 API keys, 30 of them belong to root. And that's really what we're trying to fix in this discussion today, is how can we kind of get rid of these things? So when you launch our open source repo, what I set up for you is I've got 2 different GitHub actions there. One of them is called long-lived credentials. Which one do you think that one is? This is the one I want you to be really careful if you run it in a public repo, because if you have put in the Terraform output from your Azure run, it's going to contain that client ID, the client's secret value, and it's going to purposely show you where you might be able to find these in a GitHub action. And then in order to run it, you have to go to this workflow dispatcher option, and it actually makes you select a yes in a dropdown that says, I understand I'm about to dump credentials out into the console here. I'm trying to make it safe for you to play around with this, but just be aware, and I'll show you where they're at. As you look through the YAML file, what's going to happen here is we're going to go ahead and read from the Azure Bootstrap, that ARM client secret. That's the environment variable that this is going to get pumped out to. And then if you look at the AZ login command, you'll notice we're passing that client secret into AZ login, which is going to authenticate to that tenant using the client ID, the client secret, and the tenant ID. So as you go in and look at the Terraform run output, you kind of expand some of the steps that it ran inside of here, you'll notice those values are being set right there in the output. So there's the ARM client secret. That's being pulled out. And if you go to the Azure login section, this is where you'll start to see those values being written back out to the screen. Do we see the creds section there? That's just an example of how these long-lived credentials can work their way into a log file or into a UI or into source code and then cause some problems. So that's the Azure side. Now, on the AWS side and the Google side, remember, those credentials are inside of the Azure VM. So as you run this open source project and you look in the AWS directory, there's the credentials file, there's some creds. That's what the VM is using out of the box to authenticate to AWS. Google Cloud, very similarly, is we drop in and look in the .config gcloud directory. We've got actually lots of stuff in there if you start interacting with gcloud. The one that we put there out of the box is called crosscloudkey.json. We dump that out to the screen, and you're going to see that private key that you could use to authenticate to Google Cloud using the gcloud auth command. So just some very simple examples as you launch that Terraform configuration on where you might find those credentials out there in the wild. Now, security pros, for a long time, we've been using lots of different tools as part of our arsenal to try to prevent this from happening and also try to detect when we find these things and then potentially do some sort of incident response playbook to deactivate the credentials. So things that I have done personally. I've used pre-commit hooks, which runs an AWS tool called Get Secrets that will block commits to version control that have regular expressions matching what Tom and Aiden search for out in those Python package indexes. So that'll try to stop them from getting into version control. Has anyone used Git Guardian before? This is a great tool. You hook it up to your GitHub org or your GitLab org, and it'll go through all of your repos and all of your commits, and it will say, Eric, you did something silly. It'll even look through all the history. It will yell at you from 2 years ago and say, in your history, you did this a long time ago, and then it'll actually go check that cloud provider API to see if those credentials are still valid, which is pretty awesome. So that's the detection. Where should we actually put them? Everyone screams, put them in a secrets manager. That could be the secrets manager service or the Azure Key Vault, or it could be HashiCorp Vault. I don't care which one. We're using the GitHub Action Secrets option in this workflow. That's where we want to store them. And then we start turning on all sorts of Defender-y things. Microsoft Defender for Cloud, AWS GuardDuty, Google Security Command Center, you name it. You've got your own kind of Wiz.io, your Orca security monitoring tools that you're looking for usage of these long-lived credentials to detect if somebody steals one and then try to stop it from being actionable. That's a lot of work, everything I just walked through, for no reason. What if we could just blow them away? Can we get around this problem? And the answer has turned into a yes over the last couple of years. And it's very heavily dependent upon which cloud provider you're working with and also kind of which SaaS services you're using here. So you've got to go through and really look at what identity provider options do I actually have as I'm going to build this architecture. You need an underlying OpenID Connect identity provider in order for all of this to work. In some cases, you can also use a more enterprise-level SAML-compliant IDP as well, but not all the cloud provider options support SAML, so your mileage will vary based on which cloud provider API you're trying to access. So as you look over this list, lots of us are using OpenID Connect these days for authenticating users. How many of you are using something like Okta or Auth0 or Azure's B2C or AWS Cognito, for example? Those are all OpenID Connect identity providers. That's great. That means you have one. It all starts with having some external identity provider available that can issue tokens that you can then exchange with the cloud provider for temporary credentials instead of long-lived credentials. In our scenario here, we're kind of targeting the second row middle two. We're talking about CI/CD right now. If you look back at that architecture, I need GitHub to be able to talk to Azure. The good news is, a couple years ago, GitHub released the GitHub Actions identity provider that will create custom scoped JSON web tokens for every single execution of a GitHub action. That was a happy day in my world. I spun through the day that was released, and I blew away about 45 IAM users that were solely there for CI/CD operations. We had one called GitHub. We had another one called GitLab. And then you've got different IAM users for different repos that have different permissions attached to them. We just blew them all away over the course of 2 months. And the reason that we can do that is because of the underlying token that is assigned or be able to be requested from every GitHub action or every GitLab CI/CD job. In order to use this, you have to understand the makeup of a JSON web token. How many of you have heard of, seen, or decoded a JSON web token before? They're not that complicated if you just take a minute to dissect it. So I've got 2 to 3 slides here just to get us all on the same playing field in terms of what this thing looks like. So there's a header. The header includes which type of token is it, which is a JWT, and then which signing algorithm was used to create the signature, which is the third part. The middle part is the payload. That's going to include all of these custom claims that describe who's using this thing. So that could be the original IDP, the issuer, the subject that was granted the token, the expiration, the groups that that subject lives in. All of those things live inside of the payload. And you've got to understand those fields in order to go in and configure this on the Azure side to trust GitHub's Actions IDP. So as we decode that header, if you take a look at the header here, there's some important things inside of this that you're going to need to know in order to configure this in the Azure ecosystem. So what's happening here is you're going to go into Azure and you're going to tell it to trust GitHub's identity provider. As a token comes into Azure, Azure's going to look in that header to figure out which key created the signature and which algorithm was used to create the signature. So we've got that right here. You know that we're using the RSA SHA-256 algorithm to create that signature, and then there's this random key ID. That key ID is what we're going to go look up on kind of a back-end validation check. From Azure, it's going to go talk to the GitHub action and say, I need the public key that's associated with that key ID. Now, where do we get the actual public key from? In order to do that, we've got to decode that payload and take a look at a couple of really important fields in there. Number one, the issuer. Who created the token? And does that surprise you that it's token.actions.githubusercontent.com? That's the GitHub Action identity provider. So when Azure gets this thing, it's going to say, there's the issuer. I'm going to go talk to that IDP to grab that public key so I can validate the signature. On the Azure side, what we also care about is who's the subject here. That's what we're going to check in order to validate that this token is actually allowed to access the API. So that subject's very important. Does that look like a really weird subject value? If you're not used to kind of the world of Git or GitHub or GitLab, that can be a little confusing the first time you see it. What that's really telling you is that there is a repo in the Puma security org called Nymeria, which is the name of that open source repository that you can go clone or fork when you're done with this. So that's a unique repository in all of GitHub. And then if you look at the refs afterwards, that refs heads main is saying this token was created during an execution on the main branch inside of that repo. So it can be scoped all the way down to an individual branch, to a tag. If I created a release that said version 1.0, I'd have a tag v1.0 in that path. It could also be an environment like dev, stage, or prod. There's lots of ways that we can scope where this action is running as, but that's how you know who this token was created for. And you need to make sure that that is validated on the Azure side, because you don't want to let the evil repo / Nymeria get access to your Azure subscription. So you've got to check that value. The audience is who is supposed to be using or checking this token. And that's something on the Azure side. Who is the token intended to be used by? So those are 3 fields in that payload that we're going to need in order to set this up. Okay, so Azure has grabbed the issuer and the key ID, and now it knows the subject and the audience. So we need to make that out-of-band verification check. GitHub's identity provider and all of these OpenID Connect IDPs have a well-known configuration endpoint out there on the internet. If they don't have that, this whole process starts to break down, because we need to go check and make sure that the issuer exists and make sure that key ID is still valid. And that's located in the .well-known OpenID configuration endpoint. So we're going to go back to that OpenID Connect issuer, and we're going to look for the JWKS URI. That's the JSON web key set. So do you see the URI right there on the top on line 2? So in order to get the public key, we've got to go into that, which is on the bottom of the slide. So we're going to go query the JWKS endpoint and say, give me the public certificate chain for that key ID, and now I can decrypt that signature and I can have the original hash, and then I can rehash the token that I've got, and I make sure they match up. And if everything's good, we can move on and trust that that token is the way it's supposed to be. If the hashes don't match, we know that, well, something bad happened. Somebody tampered with it, it was compromised in transit, et cetera, and then we just stop the process right there. So at this point, we've dissected the GitHub token, and we know how Azure is actually going to validate the token. All we need to do is go into Azure Active Directory in this example, or the IAM Identity Provider, or Google Cloud Workload IDP. We're going to look at all of these for the record here. And what we're going to do is configure that trust. So as you take a look at our version 2 diagram, what we want to do is go into Azure and configure AD to trust the GitHub Action Identity Provider. So we're going to put in the GitHub Actions issuer, the expected audience that I showed you in the token, and the subject that's allowed to access this service principal, and now only that GitHub action is going to be able to access our Azure subscription. So let's start with that first. And then what we'll do is kind of reverse engineer the right half of this slide, where we set up the AWS Identity Provider and the Google Cloud Workload Identity Provider to trust the Azure VM. So let's take a look at Azure first. What we're going to do is go into the same service principal, that app registration, and instead of setting up a client secret, we go to the federated credentials section and we enter the values that I just showed you inside of that token. So in order to make sure this is set up right, do you see what we have the issuer set to? Okay, now the GitHub Action IDP is the one that's expected to be sending tokens in to get credentials for this particular service principal. Do we see the subject? Be careful with that subject. That's really important, because if I leave that empty Or if at some point they allow a wildcard to go into that field, what did I just do? I just granted access to every single repository in all of GitHub. That's probably not what you meant to do. So that subject is really important. And then you see the audience at the bottom. So that's how we're adding constraints to that JWT. If everything goes well, we can then turn around inside of the GitHub action. We're going to first query GitHub Actions identity provider and say, can you create a token for me for this action that's running right now? That's going to give you a JSON web token in that GHJWT environment variable that I said on the top part of the slide. And then we're going to go down and log in with it. So instead of using that client secret, here's the big difference between where we started and where we're at right now. Instead of passing a client secret argument, we're going to pass a -- federated token argument. And that federated token is going to be sent to the Active Directory tenant, and it is going to validate the issuer, the subject, and the audience on that token. And if everything checks out, we're going to get back a temporary credential that's going to allow us to run that Terraform job. Those credentials, now they're semi-configurable depending on cloud, live for roughly 60 minutes in all of these clouds. Are we seeing the advantage here? It's a moving target. Now, every time the action runs, it's going to get a brand new credential in this scenario, so it should be different every single time as well. So if I accidentally dump that out to the screen or into a log file, et cetera, the attacker has to find it within 60 minutes in order for it to be worth anything. Otherwise, they're going to find it too late and they have no access. It's going to be access denied. The token is expired. It's no longer valid. So here's your second GitHub action called federated identity. Do you think this one's going to be a little bit better about how it authenticates to Azure? Notice I've got no client secret in this one. That does not exist in this ecosystem. So we've got a tenant ID and a subscription in the client. And as you go all the way down to that Azure login action. So there's the AZ login command. Notice we're passing it the client tenant subscription. There's no client secret going into that. Under the hood, that's going to request that JWT from the GitHub action, and it's going to use that to authenticate and then run Terraform. And you can hunt through all the output when you spin this up on your own, and you will not find a client secret on that side, which is great. But yet, if you scroll all the way down through all the noise, there's a lot going on in here. You go to the Azure login section, what you'll see is it says, I'm using OIDC authentication. Here's the federated token details, and it tells you, here's the GitHub action issuer, there is the subject that I set up in here, and you'll see login successful. So it just traded the GitHub JWT for an Azure credential, and then we run Terraform with it. Perfect. That token is valid for a very short period of time. Are we feeling a little bit better about at least the GitHub to Azure connection at this point? Awesome. We've killed one long-lived credential today. We've got 2 to go. With 20 minutes to roll here, I think we're going to be just fine. Okay, so let's jump off to the next piece, which is, okay, GitHub's out, right? GitHub's IDP is not the one that needs access to AWS and Google in this scenario. We need that Azure VM to be able to access AWS and Google Cloud. How do we do that? Now, this requires a little bit of knowledge about how the Azure cloud works internally, but Azure itself is a massive OpenID Connect system. Every Azure API typically authenticates with a JSON web token. Do you remember that instance metadata service I talked to you about for a minute? If you go to that metadata service with a managed identity assigned to the virtual machine, so that is me creating an object or a principal in Azure AD and assigning it to the VM. And if I talk to the instance metadata service for the VM and I say, can I have a temporary credential, please? If you decode it, you have a JSON web token signed by your Active Directory tenant, that's the issuer. you can pick the audience. Do you see the resource that's in bold on this slide? So I can choose what I want that audience to be, which is awesome. In a lot of cases, that could be something like https management.azure.net or keyvault.azure.net. But now I'm changing it to this random API : Nymeria workload audience, because that's what I'm going to validate over on the AWS side and on the Google Cloud side. So you need to understand how to get those tokens, and then you can reverse engineer it a little bit. So let's take a look at what's inside of that thing. So if you grab that token and you decode it, step one, who's the issuer? sts.windows.net, that's their security token service. / some random UUID, what the heck is that thing? That's your Azure AD tenant. So now you know all of the tokens coming into AWS or Google are going to be signed by my Active Directory tenant. That's a good start, right? Okay. The subject, what is that random UUID on line 4? That's the managed identity principal object ID that's assigned uniquely to this version or to this virtual machine. That's lovely. Now on the AWS and Google side, I can say only tokens assigned to this particular VM are allowed to access these APIs. And then the audience, I don't really care what you call that. Remember, that's controllable from that metadata service invocation. You just have to know what it is in order to set up trust over on the Google and AWS side. Do we have everything we need to go set this up in the other clouds? Heck yeah, we do. Let's do it. Let's kill off the other credentials. Let's start with AWS. How do we destroy the creds in AWS? All right, you're going to go to AWS IAM. You're going to go to the identity provider section, and you are going to create an AWS identity provider that trusts that issuer from stswindows.net, your AD tenant. You're going to say only tokens with this audience are allowed to come in here. And then you need to set up an IAM role trust policy that only allows tokens with the subject of your virtual machine to access this role. That sounds fun, right? It's not that hard, trust me. So we've got 2 different configurations to make here. Step 1, set up the AWS identity provider. Does this look familiar? This one supports SAML, by the way. So you could do this with just your Okta SAML provider as well. But we're using OpenID Connect because that's what the Azure VM has. We've got a JWT in there. So we're going to put in the issuer, stswindows.net. Does that look familiar? Okay, cool. How about the audience? Does that look familiar? Awesome. So at this point, anyone with a token from your AD tenant with that audience is allowed to get past the AWS identity provider. Do we have a little more work to do here? We need to constrain based on that subject. So in order to do that, you've got to go create your AWS IAM role that is eventually going to have permissions to read the data from S3, but we set up a trust policy on that. Who is allowed to assume the role? The first one is the federated principal. So what that says is that identity provider that I just created earlier on the previous slide, that's the unique Amazon resource name for that, the ARN. So we're going to say anyone that has that issuer and that audience is allowed to assume the role, but do we see the condition at the bottom? This is where all of the power and potential to horribly screw this up is in the AWS world. So make sure you check these conditions. That's where we're taking a claim on the token and we're adding an additional constraint. In this case, I'm saying the subject is that principal ID, the object ID in Azure Active Directory. Okay, cool. Do we feel better? Now that VM can assume this role using the JWT that you just pulled out of the metadata service. So we run AWS, STS, assume role with web identity. You're going to have to give it the role ARN, so that full ARN to your AWS account and the role name. And then notice the -- web identity token. That's the JWT from the metadata service that identifies your VM uniquely. That's going to return temporary credentials that live for whatever you specify. There's a duration second switch on there, and if you want them to be valid for a minute, you can do that. That might be a little low. You can make them valid for 15 minutes, 30, you pick. So that's what that's going to look like here as you get everything set up and you start to walk through that workflow on the Azure VM. So here's the command that the repo will walk you through. Grab that JWT from the metadata service. That's step one. Let's run some fancy JQ and decode that thing and make sure the values are what I told you they were. Notice the audience. That's the audience that was in that resource parameter. There's the Azure AD tenant issuer that was for the tenant that I ran this from. And then there's the subject. So I've got those three unique identifiers. Next up, let's assume the role. Now, I got a couple of things. I need to grab the role ARN. So I stuffed it in this little shell script that populated an environment variable for you. So you need that ARN in order to assume the role. We'll export that into the 3 AWS environment variables. So there's a little bit of bash kung fu here, but that's assuming a role, setting 3 environment variables. Now if I run STS get caller identity, you're going to see the magic. Who are we going to be authenticated as now? Notice it's the Nymeria Azure VM role with that Nymeria demo kind of session ID on there. That means we've exchanged the JWT for temporary AWS credentials, and now we can just run the AWS S3 CP command. I can go grab that data from storage, all without using those long-lived access keys. Check the box on number 2. How are we doing? This is addicting, right? Oh my gosh, you can go through and just blow all of these away in your org. It is so fun. All right, last one. Google Cloud. So how do we do the same thing? We need to federate access from our Azure VM into Google Cloud to talk to GCS. That's all part of the AWS IAM and admin service. You're going to go into the IAM and admin service and find the workload identity federation option. Inside of the workload identity federation option, you're going to create a workload identity pool provider. That workload identity pool provider is going to ask you for those same token attributes. What's the subject? What's the audience? And then what you can do is actually set up some custom claims to parse out of the JWT so you can perform that additional constraint on the subject. Once you get all that set up, you then say, these subjects in the identity pool are allowed to impersonate this particular service account in Google Cloud. That service account will have access to read data from the Google Cloud Storage bucket that we have set up there. So that's the last part of our architecture. So as we jump in, let's take a look at, this is a subset of the screen. I couldn't fit it all on the slide. So you have to go through and play with this or look at it once you get it launched into your Google Cloud project. But same scenario. Who's the issuer? Your Azure AD tenant, right? That's your issuer. Notice the audience. The piece that's not on here is an extra little section where it says which claims do you want to parse out of the token into custom attributes. You have to set the subject. They require you to do that. So it'll say attribute.sub equals google.subject. That's part of the default setup. But if you wanted to validate based on a group claim or some other custom claim in your token, you've got to go add those in there in order to be able to filter on that value in the next setup as we impersonate the service account. So after you've got the IDP, the Workload Identity Federation piece configured, you're going to go into the identity pool and you say, here's a service account that I want to grant access to principals inside of this identity pool. Do you see the options there? So here's my cross-cloud Azure VM service account, and then I've got a choice to make. Do I want to allow all identities in this pool to access this service account? I can't answer that one for you. That's up to you. It depends what your requirements are. In this case, remember, we only want the one Azure VM to be able to access the service account, so we say only identities matching this filter. I'd hit the drop-down, I pick the subject, I enter that subject identifier. That's our unique service or managed identity service principal ID, the object ID from Azure Active Directory. We pop that in the box, and now we can play the same game from the Azure VM out to the Google Cloud project. Now, Google Cloud is a little bit different here. In AWS, you had to deal with the trust policy, and you ran that STS assume role command. In the Google world, they tried to make it more simple, but in my opinion, what they did is they abstracted away a lot of the magic from you. So what you would do is you go to that service account, and it asks you to download this client configuration file. The client config file has all of the things that the command line interface needs to trade the JWT with IAM and get back a temporary credential. So if you dig into that file, which I'll show you here in a moment when we do the little video demo, you'll see that it's got the workload identity pool ID in there. It's got Google's security token service endpoint in there, and it also has the credential source in it. So you'll see in this example, we know we want the credential to come from the Azure Virtual Machines metadata service. So do you see what it's doing there? It's got the URL to the metadata service. That's the curl command that I ran manually on the AWS side. I don't have to do that with Google. You set it up in this config file, and then you just say Google gcloud auth login, and notice I'm just passing it the path to that client configuration. And that's when it will go do the magic and exchange the credentials out, and you'll be able to access GCS. So let's watch our demo on that side. So I've got a couple of different values. One, I need to know the Google Cloud Project ID, so that's in that file. Also, the name of the bucket that I'm going to pull the data from. So we pull those into environment variables. Next up, here's the real client config file. Let me pause this for a sec so you can actually take a look at the full thing. Notice that we've got the workload identity pool, the full path to that in there, so that's how it knows which pool to authenticate to. The token type is a JWT. They also support SAML, so that could be different depending on how you set up your identity pool. In this case, it's the OpenID Connect JWT. The token URL, that's Google's security token service endpoint. The service account that I would like to impersonate, and then you finally get to that credential source where we're going to say go to the metadata service, grab that JWT, and then go in and assume or impersonate that service account for me. So all of that's in there. If you look at the Terraform that I put into that repo, I construct that dynamically on the fly for you, so it's just a Terraform output. You can just copy it if you want to take a look at what's in it, or it also just gets magically pushed out to the Azure VM as well. So all you've really got to do when you get on there is just run this command, and it will say, oh, good job, Eric. You configured the workload identity pool correctly. You have authenticated to the identity pool. Now we need to actually access GCS inside of that project. So we set the project ID, and here's where the excitement happens. So we'll run that gsutil command. At this point, it authenticates as that service account, grabs the data from GCS, and again, we've played the same game. We've killed another long-lived credential off in the world for one that expires in roughly 60 minutes. So lots to take away from this. Is anyone surprised that I'm going to tell you what you should do next week is inventory all of the long-lived credentials in your org? We have all of our inventory, right? That's the easy part. And then just start killing them. 3 to 6 months, start figuring out, do I need to build my own IDPs? Do I need to reuse a GitHub or an Azure one? You've got lots of options there. Just start rebuilding those architectures and then deactivate them over and over and over again. So with that, my friends, lots of references in the back here. all of this information, GitHub and GitLab alone have pushed us a lot further in this space. They've made it way easier to do this. So that's a great start. And then also special thanks to some folks that pioneered different bits and pieces of this research. Aiden, Ryan, Prashant, and Brad have all done a lot of research, whether it's with GitHub or AWS or with Google Cloud. So go through and read those resources, and you're going to be ready to rock and roll. Go kill your long-lived creds. Make the world a safer place. With that, I will set you free if you need to head out. Thank you for coming back inside. I know it's gorgeous outside, so I'll be around for a bit if you want to chat and ask questions.